we go. Okay, so yes, I'm going to give a brief talk, and then I guess as I hear people have questions, I'm going to sort of throw it open to questions following the talk. And yeah, so this talk today is not so much an introduction to ASIO in a tutorial form, because there's good documentation for that. This is more to give you a bit of a sense of the thinking and philosophy that went into ASIO, and it also drives my use of it in the work that I do, and may apply to the sort of things that you do. So one of the things I find when you talk to people, and particularly Java programmers, but okay, so with C++ people here, is when we hear the word concurrency, when people mention the word concurrency, the thing that comes to mind is threads. That the way to solve problems that involve concurrency is to throw threads at the problem, and depending on what language and environment you work in, that may be encouraged. But what I want to sort of try and tell you today is that actually threads are an illusion. Okay, that was kind of a bit of flame bait. What I really mean is that threads are just an abstraction. Okay. So what is a thread in a nutshell? And I'm talking in terms of using threads to perform networking or other event-driven related tasks, where what you're really doing is using the threads as a mechanism to coordinate your network operations. So really, your thread is a state machine, and it's a state machine that's implemented using these things here. So it's got a stack frame, it's got some thread local variables, has registers, it has the code, the sequence of instructions that's going to be executed as part of that thread, and it's got the program counter, which is that, if you like, is the thing that captures the current state of the state machine. It's where you're up to in the thread. The important thing about this, though, is the threads are really a general purpose abstraction. Like, they're designed to solve a whole lot of different issues, not just forming blocking network I/O, but also to allow you to parcel out CPU-bound work across the hardware, the CPU cores in your system. And so it's trying to actually address a whole lot of different use cases with a single general purpose abstraction. The point when it comes to networking, so if you know about the problem that you're working on, then you can usually do better than a general purpose abstraction. And so specifically networking and other event-related I/O tasks are a case where actually I say it's easier to do better than threads. So what does that actually mean? Now, many times I've gone and talked to people about ASIO. I remember distinctly when I was at the BoostCon or something, people asked me, but hang on, I'm quite happy with threads. Typical design people like to use this thing called thread per connection. Now, this is like, for the purpose of example only, this is ridiculously trivial. Like, any sensible program is going to be a lot more complicated than that. But what we have here is a single thread with one task, which is to go and read bytes of data off a socket and then just do something with it. Like, maybe it's some sort of HTTP protocol parse or queries to run against a database. It doesn't really matter. The point is that you've got a thread that's dedicated to handling just this single connection. So what are the implications of that? Okay, so here's what happens. This is a bit simplified, but for the purpose of thinking about networking I/O, this is more or less what happens when you do this code, right? So your thread is performing this. This is an asio function read sum, which just blocks to read bytes off the socket. So the first thing is your thread is in this running state, and it performs the read sum call, which is an instruction to your operating system's network stack that you want to go and read some data off the socket. The data's not there right now, so your thread goes to sleep. So your operating system's now just got this thread sitting there in this sleeping state. Now, sometime later, somebody sends you a request. Now, what happens then? So, if it's Ethernet, say the frame arrives on the network card. The network card triggers an interrupt to wake up the network driver. The network driver does whatever it needs to do to decode the particular protocol for that network. Then it passes the data onto the network stack. The network stack does what it needs to do for TCP or UDP or whatever the high-level IP protocol is. And then, right at the end of that, there's a context switch to wake up what was your sleeping thread and put it in the running state so that it can then go and do something with the data that just arrived. So the first question, when people go, oh, I love thread per connection, first question I like to ask them is, okay, what happens when the number of connections exceeds the number of CPUs or CPU cores that you've got in your machine? So, very simple case here. I know these days we've all got machines with 16 cores in them or something, but let's pretend we've got a single CPU machine here. We've got two threads which are performing reads on two different sockets. Okay, so what happens when your packet arrives? So let's just say multiple frames now arrive at the same time. Your NIC passes multiple interrupts, probably, to the network driver. The network driver passes the data onto the network stack. The network stack now wants to deliver the data to the threads and wake them up, but it's only got one CPU, so it can only wake up one of the threads to run. So the first thread wakes up, and it does something with the data, whatever it is, database queries, parsing doesn't really matter. And then, because if you remember, what I had before was a very simple loop where I just called read on the socket indefinitely. That thread calls that subsequent read sum, and only then does the network stack get to trigger the second thread to wake up and then process the data that it was waiting for. So what happened here is essentially a queuing problem when it comes to reasoning about performance. We had two tasks that were ready to execute at the same time, which is to process the two packets. And we could only do one after the other. Now, the cost of running each task includes the context switch to the threads. Now, in terms of scale, it depends very much on the operating system that you're working on, how expensive the context switch is. But generally, it's measured in tens of thousands of, or thousands of CPU cycles, like equivalent to instructions, right? So it's actually quite an expensive operation compared to just reading and writing values from your local variables and so on. So even though in that example I was only talking about what if you had two connections, it's just a general problem. What if you have n ready connections where n exceeds the number of available CPUs? Okay, so the effect of this is detrimental potentially to both the throughput capability of your program and the latency. So you think about what happens for your program to process those two frames that arrived on the socket. It involves all the code from the passing the data up, and then it has the context switch, come back, context switch a second time, and then it's processed both of the packets. And the thing to realize here is that there are particular costs here that we can actually we can spread across both of those packets. And in this particular case, it's the cost of a context switch. If we were able to process the two events in a batch, then we get to spread the cost of the context switch across the two. So we in this example, we get to cut out one of those context switches. So as I said before, the thing to remember when you're using a thread to coordinate your network I/O, really all it is a glorified state machine. Okay, if you realize that, then you can realize that there are actually other ways of writing state machines in code. You don't have to go straight to a thread. And so that is really the purpose of asio as a library, is to allow you to coordinate things like network I/O using other forms of state machine. So what I've got here is a very, very simple asynchronous equivalent of the thread per connection program that we saw before. Okay, now so for people who aren't familiar with asio, I'll just run through the elements of this program. So we have the socket, which is just an abstraction over the socket APIs presented by the operating system. And in this case, we're going to use a standard array as the buffer to read into. Now the reason these are class members here is, unlike with the thread where you've got a stack and you have control over the lifetime, we now need to explicitly manage the lifetime of things that are involved in the asynchronous network I/O. So what happens? The actual asynchronous operation occurs in this member function do read here. So what happens is on the socket we start off and we call this member function async read sum, which is the asynchronous equivalent of the blocking read sum that we saw earlier. And we pass in the array that we want it to read the data into, but this time we have this additional parameter, which is a callback. In this case, it's a lambda. And this is called when the asynchronous operation completes. So unlike blocking one with a call would block, this async read sum call will actually return immediately once the asynchronous operation has been initiated. So then time passes, and then when the data arrives, callback's called and it's passed an error code to tell you whether it succeeded, or if it didn't succeed, to tell you what the reason for the failure was, and it tells you the number of bytes that were transferred. Once we've got that, the next step is essentially equivalent to the blocking. We just do something with the data, but this time we don't have an explicit loop where I think I had a for loop or a while loop before to go back around and start the next operation. In an asynchronous world, we need to chain the callbacks. And so here, once we've done something with the data, we then go and call do read again, and that comes back around and then kicks off the next asynchronous operation. So even though it sort of looks recursive, it's not actually recursion in the normal stack sense. But what you do get is a chain of asynchronous operations where the first async read starts, when it completes, it then initiates the next one, and the next one, and the next one, and so on, until the connection is torn down or forever, potentially. Now, the thing down the bottom here is this thing called IO service run. Now, the IO service object in asio, in more general terms, it represents your link the link between your program and the operating system's network stack, if you like. But specifically in this program, it's acting as the event loop. So when you call run on an IO service, it blocks while it processes all the events associated with the asynchronous programs. So, well, I've left out a whole lot of code here, but this is the sort of thing you would put in your main function to drive event processing of the program. Now, if we go back to our example before where we had two connections running on our single CPU machine. So, if we just go back and code, we have two independent session objects that are performing the asynchronous network I/O simultaneously. So what happens now is your frames arrive at the NIC interrupts, generates interrupts, and the network driver processes the new frames, the network stack has passed data, and then finally it only has one thread to wake up, so there's one context switch now, and once that thread is woken up, it runs both of the asynchronous completion handlers. So one for the first session object, and then when that is finished, the one for the second session object. You go, oh, hang on, I mean, are we really doing a context switch anyway in here between session objects? What do we, have we actually gained something? In practice, yes, you have, because whereas before we were using threads to represent each session, and then you had a context switch from one thread to the other, and that's measured in thousands of cycles. A dedicated event loop, which is managing the state machines purely through fallback objects, can switch between the different state machines in tens of cycles. So we're talking about 2 orders of magnitude difference in cost. So what we now have to process both of those frames is we've cut out one of those context switches. Now, this is only 2. If you scale up to n ready connections, then saving is essentially n context switches for in one time. So I talk to these people who love their thread per connection stuff, and the next question I usually get is oh, hang on. I know that I only deal with a small number of connections. So I still really don't want to use this asynchronous stuff. I'd rather stick to my my thread per connection design. So then, okay. So here's some things for you to consider. So first of all, okay, what happens when everything's good? You've got 2 CPUs and 2 connections. So now what happens when data arrives at the NIC generates interrupts, the driver presents the packets to the network stack. Now the network stack wakes up 2 threads, which are now running on 2 different CPUs. So these last 2 steps here happen in parallel. So in terms of the time taken to process those 2 packets, we've got our saving in terms of total absolute time, because these 2 expensive context switches at the end here are happening at the same time. So what's wrong with that? That's fine, isn't it? Okay, so the first thing to consider is whether or not your 2 threads, your 2 session connection implementations are actually independent. Now, in this very simple echo program, yeah, okay, that's fine, but this is a trivial example. Only certain sorts of problem truly have these independent session objects. You'll often have them accessing some shared data structure. Maybe they've got the one database connection to process queries on. There's often something that's shared between them, which they both need access to. And if you've got multiple threads accessing a shared resource, the typical solution to that is to use a mutex. So what happens then is when the packets arrive, the network stack wakes up both threads. But only one of the threads is able to acquire the mutex immediately so that it can access the shared resource. And the second one is unable to and is then blocked again until the mutex is released. So what happens now is that saving where we got to run these two context switches in parallel is lost again when this one goes to sleep. Now, if we had written this program using an asynchronous model instead, then the thing is that both of our events are run in the same thread. So we don't have the case where both are running simultaneously, so we don't even necessarily need to have a mutex at all. We've confined all of our application code to run in the one thread. So when we run the first event and we do something here accessing the shared resource, we don't need to do any locking. So there's no, and then it comes back around and runs the second session's event. It's guaranteed not to be running at the same time as the other one. So it doesn't need to do any locking. It doesn't go to sleep again. You don't have this additional penalty of a context switch. And so you aren't paying that extra cost. Now, a similar problem, one that's not exactly the same, is you should consider whether or not your thread per connection model is actually only one thread per connection, because many of these systems have to deal with both inbound and outbound data simultaneously. So we have typically one thread which is performing the reading, waiting for data to arrive. We have a second thread which is perhaps dequeuing packets off or messages off some sort of shared queue, and it's then going and writing the data to the socket. And these two threads are performing the functions associated with a single connection, and again we have this shared resource, so we need to protect that shared data with mutex. And we have exactly the same problem as we saw before, where both threads may get woken up because we simultaneously can write and read, or whatever it is that they're doing, and the second one, when it's woken up, is unable to acquire the mutex and goes back to sleep. Now, once again, in the asynchronous case, we don't have that problem because we've guaranteed that there's only one thread running all of our networking state machines. So we still don't need the mutex to access the shared state. We can have multiple chains of operations associated with a single session. Now, the screen's not big enough, so I haven't got a full listing here, but you can imagine that in addition to this do-read function, which is responsible for the chain of operations to read the data off the socket, we might have a do-write function, and we might have another function to do with sending heartbeats, another one to determine whether or not we need to terminate the connection because it's been idle for a certain length of time. We can have all of these state machines that are working together to manage the overall session, but we still don't need to have a mutex to protect that shared resource. Now, this is where it gets a bit more interesting for the sort of stuff that I work on. And that is, okay, what if we consider the penalty associated with interrupts? Now, in a typical server-based machine, these days, what will happen is you'll have an architecture where you have two physical sockets or more, and each socket contains multiple cores. Your network card might actually be closer to one of those sockets than the other. So in terms of data arriving off the network, not all CPU cores are created equal. It might be more expensive to pass the data across to a core running on one socket than the other. So what happens there is when your data arrives, okay, the first thread in our thread per connection model, everything's fine for it because all the data is already, when I say local, I'm using that as a term to cover the cache, but also on newer architectures, you can have actual memory banks, RAM, that's also closer to one CPU than another. The operating system might have already put the data associated with those packets in a location that's fast for thread 1 to access, but it's actually really quite expensive for thread 2 to access, because thread 2 might be running on the other physical socket. Now the nice thing, when you start running things asynchronously, is that it's actually really easy to change your program so that it can be pinned to a single CPU. And it's still processing events from multiple sessions, but when those events arrive and it processes those packets, we've guaranteed that, so this is like a Linux specific call here, but you can do it for your operating system of choice. We're guaranteed that our code is running on a particular CPU, and we can then go ensure that our machine is configured so that the interrupts from that network card go to a particular physical CPU, and then our code to process the connection also runs on the same CPU.
That will also be standardized then?
Which bit? So you don't even necessarily need to add code to do that. Depending on your operating system, there may actually be, like on Linux, for example, there's task set or NUMA control. So there's ways to actually, external to the program, ensure that your code is running on a particular thing, right? And the problem is, if we'd written this program using thread per connection, we've again, okay, maybe we've got a 16-core box, but we have to deal with 10 running across 2 physical CPUs. We have to deal with 10 connections. We can't, we can't guarantee that they'll all have a CPU available to run on if data arrives for all of them at the same time. Some of them might end up running on the either running on the other socket, or we go and set it so all of them are confined to the same physical CPU. But now we've got the queuing problem again, because one of them might be running on the CPU and it's not going to give it up, and the other one has to go to sleep until it's available. Now, little bonus, depending on what sort of area you work in, is actually we can eliminate the cost of context switches altogether. It's not good for the environment, though, I have to say. We don't have to change this code. This code remains exactly the same. What we've done is change how we drive the event loop. So previously, we had, I don't know if you can see it down the bottom here, but there's a call IO service run. Now in ASIO terms, when you run the IO service, it blocks. So if there's no events ready at that point, then it just goes to sleep. And then when the events arrive, there's a context switch to wake it up. Now poll, on the other hand, does not block. If there's no events available, then it returns. The thing is, we can actually just run that in a tight loop. You go on. Didn't have any events available, let's try again. And I think that might be the definition of insanity, but actually in this sort of program, it actually makes a big difference. So if your thread never goes to sleep, then it never pays the context switch cost associated with waking up. It's essentially asking the network stack all the time, have you got any data for me? So this is sort of what happens. So you've got this thread just sitting there continually hammering the network stack. You've got some data. When data actually does arrive, it gets passed up, but then it's just kept there temporarily, waiting for the thread to go and just take sort of hold it and take it. Now the thing that this allows you to do is, depending on the hardware you've got, you can actually bypass the kernel altogether. Now, depending on where you get your network cards from, some of them actually come with what's called the kernel bypass layer, and it is essentially a way to get the data off the network card directly without going through the operating system network stack. And depending on which one you use, and that, say you're on Linux, some of them they come, I don't know if you're familiar with like LD preload, but there's ways where you can replace the functions provided by the operating system with your own custom versions. So when you call read on a socket, normally it would be calling the operating system version, which goes to the network stack. When you run with this kernel bypass layer, actually what happens instead is it's hooked the function, and instead of going to the kernel network stack, it then goes and uses a vendor-provided implementation of the network stack, the IP stack. Potentially uses DMA or something to access, so the NIC will copy the data to memory for you, and your program then reads that data directly. Now, the advantage of this is that, okay, well, I was talking about context switches before, but even interrupts and things are expensive. If we use a facility like this, we've eliminated interrupts completely from the system. We've just got data arriving in the NIC, it's just copied into some memory buffer somewhere. We've got our thread, which is just spinning away on that whole function, never sleeping, taking the data off. And that, that is basically, in terms of things like latency, this is how you get it as low as you can, but it does come at a cost because your CPU is running at 100% like maximum power all the time. Okay, so that section as well, I was just trying to give a bit of an overview of the thinking that you might want to, like, when you use something like ASIO to implement your network stuff, it actually pays to think about what's happening underneath. Okay, so if you think in terms of data arriving at your network card and interrupts and so on, then it's actually you can do much better than threads in performance terms like latency and throughput. But how would you actually design your programs to take care of, to make use of that? So this next section I'm just going to run through very briefly. If you're going to use ASIO, for the preferred approaches for designing your system. Now, it helps to have a concrete use case to explain these approaches. So what I've got is a very simple TCP proxy. So unlike our previous example, we've just got something reading off the socket. We've now got something that acts as an intermediary between the client and the server, and its job is purely to pass the data through. And use cases for this might be to get through firewalls or data inspection or whatever. Essentially, your sessions are responsible for transferring data in both directions simultaneously. So what the specific steps are, proxy is just sitting there, it's waiting for a client to connect to it. When a client connects, it goes and establishes a connection to an upstream server, and from then on, it's transferring data in both directions. Okay, so here are the recommendations that I would suggest in order of preference. So I think, I don't know where I read it, I think there's general advice for using STL containers that vector should be the container default choice.
Yeah.
So when it comes to this sort of thing, single-threaded should be the design model of default choice. Okay, and that's simply the reason that you don't have to worry about explicit locking and so on. So you're less likely to make errors when you introduce brace conditions because you forgot to protect access to a shared variable or so on. Everything's running on the one thread. Okay. Now that I've got this 1.1 here, which I'm going to talk about. Well, okay, maybe it's a variant in single-threaded case where you might need to deal with longer-running tasks and how to manage that. And then I'm going to run through these two multi-threaded design approaches. Okay, so single-threaded we sort of already seen. And I said I would recommend this as the preferred design option, but there is a limitation. Okay, you need to remember to keep all of those completion handlers, like the callbacks, you need to keep them short and non-blocking. Because what's going to happen if one of those handlers goes and tries to write to a database that's heavily loaded? If that blocks for a few seconds, no other sessions are going to be processed. So you do need to take care in all of your handlers. You need to pay attention to what they're doing so they don't go to sleep and block everybody else behind it. So what does our program look like? So this is, I've structured the code this way to make it a bit clearer how the state machines, if you like, that make up the program relate to each other. So what happens, step one, we've got this accepted and async accept. So what we're doing here is we're doing an asynchronous operation to wait for a new connection to arrive at the server. Okay, when that completes, so the ... is actually this box. Right? When that completes, if there's no problem, then we go and we want to establish our connection to the upstream server. So that's the async connect. Now when the async connect completes, and if it succeeds, at this point, we're creating two separate state machines to process the data in each direction. So we have one which goes in a loop, so it started off by doing an asynchronous read from the downstream socket. If that succeeds, it then starts an asynchronous write to the upstream socket. And that succeeds, then goes back, just read more from that one, and so on, round and round and round. The other half of the state machine, if you like, is going in the other direction. It's reading from the upstream and going to the downstream. And again, it's just going round and round. Now these, as we saw before, they're all running on the one thread. So we don't need to do any locking. If we had some shared data in here, they don't need to do anything. They're just, each little parcel of work here in each box is guaranteed to run only one at a time. But we do have reads and writes that are happening simultaneously. Okay, so version 1.1 is, okay, well, I can't always guarantee that my handlers can be short and non-blocking. I may have tasks that are going to take some lengthy period to execute. What do I do then? So my recommendation is to keep the networking related code still single threaded, because there's often a lot of complexity there with your state machines to manage the connection, and just pass the long running task to some background thread or thread pool or something like that to perform the task. And when the result is ready, then we pass that result back to the thread that's performing the network IO, and we resume with the next step of the state machine. So if we take, for the purpose of this design approach, I'm just going to modify our use case slightly. I'm going to add this extra step in here, which let's say that once we've accepted a new connection from a client, we need to go and check its IP address against some whitelist, but the whitelist contains potentially millions of addresses, and it's running on a database server, in the next city. So you don't know how long it's going to take. So, and only when you get back an answer in the affirmative do you get to then make your connection to the upstream server. So I'm not going to show the entire state machine. I'm just going to insert this new step in between the connect. So in between the async accept and the connect. So now what happens when our async accept completes, and if it's successful, what we're going to do is we're going to post the next step to our thread call. These are functions in ASIO, by the way, in the latest version, but you can use your own thread call, that's up to you. You post it to the thread call, you do your long-running work in the thread call. When that's done, then you need to go and you post the result back to your network thread, and then continue on with the rest of the state machine as it was before. Now, obviously, there is a downside to this, which is you're now paying a context switch for each step in this direction. Okay, so you need to take into account that you've traded off this long-running task, kicking it out of your network thread, but you're now paying a higher cost in passing that work to the thread call. So you need to work out whether or not, what is, for your particular use case, what do you consider to be too long running? Okay, so if your requirements are such that all connections need to be processed within tens of milliseconds or whatever, then any task that might take multiple seconds, you should probably consider passing off to this background thread. Okay, but what if that's not acceptable? Okay, so here's one approach. So when keeping in mind that this is in order of preference, my recommendation. So the next one, what we're going to do is we're going to run multiple IO services. Now the IO service represents the event loop. Okay, so we're going to run more than one of them, and we're going to have them spread across the multiple CPUs in your machine. Okay, so now what happens is when a new connection is accepted, it will get assigned to a particular IO service. So you need to be able to partition the session objects in some way. And I have examples in ASIO where we do it round robin, but you might have other better, smarter ways depending on your application. Now the advantage of this is now you are actually spreading this workload across multiple CPUs, but what might happen, generally you should still keep your handlers short and non-blocking. If they do block, you'll now only be blocking the ones on a particular partition, a particular IO service. The other ones can still execute concurrently, but you're now making use of more of the hardware in your machine, more of the available CPU power. Now, okay, so when would I recommend that you actually make this, switch to this model? I would say for most applications, you probably don't need to. If the processing associated with your network state machines is such that it's now consuming 100% of one CPU, then okay, so now you've reached a point where the running those on a single thread is a bottleneck, and you may want to consider moving them out to run on multiple CPUs. Alternatively, maybe it's not a resource limitation, but maybe a latency requirement. So there's too much load being assigned to the one CPU. And so queuing occurs, you're not responding to messages in a timely fashion because there's too many items in the queue. So by spreading the load across multiple CPUs, you're able to respond to those more quickly. The other limitation is you should probably, rather than using shared resources that are shared between the partitions, you should stick to a message passing kind of model so that you don't end up having one of your partitions sort of blocked, waiting on a mutex, waiting for the other one to complete. You try and keep everything asynchronous, even the communication within the objects within your program. Okay, so the thing about that model, sorry, the title change, but the thing about that model is that we didn't actually have to change our program at all. Our TCP proxy was still essentially single-threaded. We had multiple single threads, if you like. So we still didn't really need mutexes or anything in each one. But the next and final design choice is where you go, okay, I'm unable to partition my objects independently. What I really want to do is I want to throw multiple threads at the one IO service. So I want my event loop to be able to service the work across multiple threads. Okay, so the problem now, though, is that, okay, everything's fine. It's the first step. You know, we do our async accept and we do our async connect. And so far, we've only got like a single chain of operations associated with our connection. But since we get to this point, we're starting two separate state machines that are now running concurrently. We now have to deal with the fact that because we've got multiple threads servicing our IO servers, these can run, these two little classes of work here and these callbacks are able to run in parallel. And we've got some shared resources, which are the sockets involved in our proxy. So this is not so good. What can we do about it? So the first thing people might try and do is, okay, well, I'm just going to protect all these things with the mutex. Okay, but now we've gone back to the problem that we had in the first place, where one of our threads might end up going back to sleep because it's unable to acquire the mutex because the other one is currently holding it. So is there another solution? So if you're using asio, that's the example before. So we've got one thread waiting on the mutex and the other one while the other one holds it. So the solution to this provided by asio is we want our network state machines to be executed by what is called a strand in asio terminology. Now a strand is it's an object that you can use to ensure that for certain groups of asynchronous operations, the completion handlers associated with them are never run concurrently, and that they run in first in, first out order. So typically the way you would use that is to say that for our proxy, we want all of these handlers here to run in the same strand. So the way you do this is when, if you're using lambdas, when you initiate your asynchronous operation, we wrap our completion handler in this strand. And this tells asio that this callback is associated with the strand, is going to execute in the context of that strand. And we do that for all of the asynchronous operations that make up this session. So now what happens is, okay, yeah, so we kick off these two parts that are running in parallel, but even if two of them are ready at the same time, asio ensures that they won't get scheduled at the same time. Now, unlike a mutex, if one of these acquired a mutex, the other one will go to sleep. What asio will do with the strand instead is, the strand is busy, I'm just going to enqueue the second handler to the back. And then when the first one finishes, it goes, oh, look, I've got some more to do, and goes and runs the other one. But the thing is that okay, so while this keeps the logic associated with each session single-threaded, you can have multiple sessions running on the thread pool, and they can still execute in parallel. So, okay, if you've got multiple, these will never execute in parallel with the same session object, but a different session object is still able to run the completion handler on the other CPU. So now what happens when the data arrives, it's passed up, the first handler runs immediately, the second handler, assuming that the event is not dequeued in the same batch, is just enqueued to the strand and waits, and this thread is then able to go on and service any other events that are available. Now, if you use this model, then actually it's okay to have handlers that potentially block for a long period. So it's really up to you how much concurrency you want to enable by how many threads you have calling IO service run here. So what you can do, if you think of the IO service here as acting as a thread pool, and by calling IO service run, what you're doing is donating a thread to the thread pool to service the network events that are arriving. Now, I just want to add one more thing to these recommendations, that whichever one of those you choose, and yes, you should, I think, generally stick to single-threaded, but whichever one you choose, it's still important to pay attention to things like the interrupts and CPU affinity. So even if you have a pool of threads processing the network events, you may, and you've got multiple physical sockets in your machine, you may want to ensure that that pool is all assigned to the same physical socket as the network card, so that when data arrives, it's actually conveniently local for all of the threads servicing that IO service. And as before, this is still something you can do without necessarily changing code. You just need to make sure that your event loop is associated with those things. Okay, so that's the end of my prepared section of the talk. Do you have any questions?